In this lecture, we're going to look at a, a technique for anti-differentiation called completing the square, which for some reason is deleted here. So I'll just write CTS, completing the square. Now, in terms of integration, this isn't really such an important thing. It's so remember we have first you do direct from the tables when you're anti-differentiating. If there's no directing, you do manipulation. If there's no manipulation, you do a substitution, which I will call a W substitution, but maybe substitution be the best. And we've got a new technique, which is integration by parts. So this complete the square falls under manipulation. It's a special manipulation. I think to me this is a very hard section. But what I would say is that if you're going into level 7, the actual manipulation that we're going to learn about is used in a different context, and it's very important. Okay, so what do we got here? The W substitution method and parts replaces complicated antiderivatives by simpler ones, but you have to be able to evaluate those simpler ones. Okay, usually you do standard tables, but sometimes to be a special manipulation. So there's 3 special ones: x squared plus that contain there's 1 over x squared plus a squared, and this usually has a square root. And the one we're interested in is this one and the first one. And they're both so we're going to look at the 1 over x squared plus a squared and this one too. They're related using Pythagoras theorem to inverse trigonometric things. So what we're going to do is we're going to see where these come from by differentiating inverse sine and inverse tan. Okay, so I think we'll do the first one. So how do you differentiate inverse sine? Where does that formula possibly come from? So what you start with is you say y of x is equal to inverse sine, and I'm going to write it this way. So inverse sine of x is equal to y, and if you do take the sine of both sides, the sine is the inverse of sine inverse, you just be left with x. So you get x is equal to sine of y. So we can just write a little kind of a bubble here. So if you have here, you're going to have angles, and here you're going to have sines. Okay, so you put in an angle here, which I'm calling y, and then x is the sine of y. So if so it says y is equal, so you do the sine of y and you get x, and inverse sine is the function that brings you back. So if you have say y is equal to sine inverse x, and you take the sine of both sides, the sine gets rid of the inverse sine as such, and you're left with x is equal to sine of y. So that's what we're looking at here. Now what we can do is we can differentiate this using implicit differentiation. So we're going to differentiate both sides of x is equal to sine of y of x. So the derivative of x is equal to 1, and when we're differentiating sine of y of x, if it's sine of x, it's no problem, but it's sine of a function of x, so we have to use the chain rule. The chain rule says differentiate the outside function. The outside function here is called sine of x, and the derivative of sine of x is cos of x. Evaluated at the inside, now the inside here is y, times the derivative of what's inside, and the derivative of y, all we can say is dy dx. And we can divide both sides by cos of y here to get that dy dx is equal to 1 over cos of y. Now we want to put y back in terms of x. Now there's different ways that we can do this. So I think I'm going to do 2 different ways. I'm going to show that cos of y is the square root of 1 minus x squared. Okay, if x equals the sine of y. So one way is to draw a triangle. So what does it say? X is the sine of y. So if you make a triangle, Now you've got, look at the top of the page, you've sine of y. So y is an angle, make this y. Okay. And you've got sine of y is equal to x. Now sine is opposite over hypotenuse, and we want that to equal x. So how about we take this to be x and this to be 1. Okay. And what we're trying to look for is cos of y. Now if we do a little bit of Pythagoras, we'll get, let's call this thing here a for adjacent. So we get 1 squared hypotenuse is equal to the sum of the squares of the other two sides, x squared plus a squared. I'm trying to find cos of y, so I need to find a. I'm going to take away x squared from both sides. So I get 1 minus x squared is equal to a squared. And I'm trying to find a on its own. Now, ordinarily, there are 2 solutions, and we will see that. So if I take this square root of both sides, but as I said, there are 2 solutions, plus or minus. But in fact, because a is a side length, I just need the plus 1. So a is equal to, that side there is square root of 1 minus x squared. And therefore we can write cos of y is equal to adjacent, which is square root of 1 minus x squared, over hypotenuse, which is 1. And any number divided by itself, any number divided by 1 is itself. So cos of y is equal to square root of 1 minus x squared. So that's one way of doing it. Another way of doing it would say that cos, you use the fact that cos squared y plus sine squared y is equal to 1. Now, you always have cos squared plus sine squared is equal to 1. You can actually see it from the green triangle because the opposite to y is sine y, and the adjacent to y is cos y. And if you just do Pythagoras' theorem, then you get 1 squared is equal to the adjacent squared plus the hypotenuse squared. That's the cos squared y plus sine squared y. Now we're looking for cos squared y, so we take away sine squared from both sides. And now we use the thing that's up the top of the middle of the page. Sine of y is x, so sine squared of y is x squared. And then we take the square root of both sides. Now there's a little bother here because technically it could be plus or minus. Now some of the arguments I used about the triangle don't hold because y could actually be an angle that is bigger than, or it's not between 0 and 90, because you do have cos defined for bigger numbers. I'm not going to worry about that too much. I think what happens is there is a property that says that, and so in other words, if you run with the minus 1, you end up, you can use a property that inverse sine, I think this is correct now, of minus x is equal to minus inverse sine of x. So if you run with the minus 1 down here, you end up with probably end up, therefore you get minus sine inverse of minus x is equal to sine inverse of x. So you probably end up with minus sine inverse of minus x, which is actually the same thing. So we don't have to worry about that. But whatever way you do it, cos of y in terms of x is square root of 1 minus x squared. So we have that the derivative of inverse sine is 1 over cos y, but cos y is square root of 1 minus x squared. And the inverse tan works similarly. And you can in fact show a little bit more, and these are the things that are in the tables. Now you can prove these by actually directly differentiating the right hand sides using the thing above and little chain rules. Okay, so both of those are in the table. So that they're examples of things that people often do a use substitution with when there's actually no need. Okay. Right. So if you have a quadratic, so that's something with an x squared, that's not a sum or difference of 2 squares. So if you have an x squared and a constant, it'll probably be inverse sine or inverse tan. But if there's also an x, you have to do something a little bit extra. Now, what you have to do is complete the square. And like, how would you know to do this? I won't spend 5 minutes kind of figuring out how would you know to do this in context in level 7 when you have to do this. It probably makes it, I'd probably have to explain it in that context how you'd know to do this, but here you have to probably be a bit more pragmatic and say, oh, this is a module where you've learned this technique, you are going to be asked to do this. Okay, so how does it work? So what you do is there's two types, so it's kind of explained here. So depending on whether you have a plus x or squared or a minus x squared. So the two different types are, if it's plus x squared, you go for a squared plus x plus b squared. Okay, and if it's minus x squared, you go for a squared minus x plus b squared. So in the level 7 context, the x going to x plus b would be called a shifting, and yeah, and so it'd be something more to the forefront of your mind, but it isn't here. Okay, so how do you actually possibly do this? So how do I write x squared, which is a plus x squared, in the form a squared plus x plus b squared? How do I possibly do that? Well, what you do is you kind of force them equal to each other. Okay, so you do what you want to do. So we have x squared plus x plus 5 over 2. We want this, so I'm going to put an exclamation mark there. That's to say that that's something that I want, equal to the right hand side. Now what I need to do there is multiply out carefully a squared plus x plus b all squared. Now x plus b all squared is something at this stage that you should be able to calculate. So it'll be x by x, which is x squared, x by b, which is same as b by x is bx, b by x, which is another bx, and b by b is b squared. So this is actually equal to x squared plus 2bx plus b squared. So we're looking to find this in the form a squared plus, what have we got? X plus b all squared is x squared plus 2bx plus b squared. And now what we do is we compare. Now what I'm going to do with the thing on the right hand side is to write it in the same order as the left. So I do the x squared first, then the 2bx, then the x in other words, and then the stuff without an x. Okay. So I have this x squared plus x plus 5 over 2. I want it to equal the a squared plus x squared plus 2bx plus b squared. And what I just said is equal to x squared plus 2bx plus a squared plus b squared. And so I want the thing on the left to equal this. So now what we do is we just go off and compare. So they both have an x squared. So no problems there. Now the question is, how many x's do I have on the left? I have 1. Because x is 1x. And how many x's on the right? 2b. So I want, if 2b is equal to 1, I have the same amount of x's on both sides. And what constant do I have on the left? 5 over 2. What constant do I have on the right? A squared plus b squared. So I need a squared plus b squared to match up with 5 over 2. And I need 2b to match up with 1. And you'll see that there's only going to be, well, actually there's two ways, but again, you're going to pick A and B. Okay, so set 2b equal to 1 and a squared plus b squared equal to 5 over 2. Now the equation on the left is obviously very, very simple. You just divide both sides by 2 to get b is equal to a half. And now that you know that b is equal to a half, you can put it in here. A squared plus, well, what's a half squared is a half by a half is a quarter, equal to 5 over 2. 5 over 2, by the way, is 10 quarters. Okay, so I'm going to take away a quarter from both sides. So I get a squared, 5 over 2 minus a quarter. Go into the calculator, whatever, you get 9 over 4. And then to get rid of the square, you can do the square root of both sides. But you want to be careful because in general with a square there are two solutions. And you can pick the negative one, but it's kind of stupid. It's not wrong, but it's no, like, Say you say, oh, I want to write 9 as a square. You can do it as 3 squared, or you can do it as minus 3 all squared. Just do it with 3 squared. So it's plus square root of 9 over 4, which you could put into the calculator and you get 3 over 2. So now we can say, and our kind of answer is, as it were, x squared plus x plus 5 over 2 is equal to a squared, which is 3 over 2. So the a squared is up in the top right hand corner of the screen, plus x plus b, which is a half squared. And you might kind of recognize a little bit of this, and you might kind of notice that actually this is where the minus b formula comes from. So you prove the minus b formula kind of, do something like this. Okay, off we go. So that's the special manipulation of completing the square. So we're looking at this antiderivative here. So let me say, first of all, there's nothing like that in the tables. Like you could say, oh, can I just antidifferentiate the bottom? Now, if it was the x squared minus 12x plus 41 dx, that's easy. You can do it term by term. Now, what you might try and do, but it's complete nonsense, is to say that this thing is equal to 1 over x squared, which is x to the minus 2, 1 over minus 12, which would be minus 1/12, 1 over x, plus 1 over 41. That would be easy, but those things, they're not equal. So that's not equal to that. And this, well, this simply isn't it. So what I'm saying on the first one is you can't just antidifferentiate the x squared minus 12x plus 41. You can only antidifferentiate term by term if there is sum. And there isn't a nice manipulation like the one below. So I'm actually going to rub out this in case anyone thinks that this is something good to do. And I should probably rub out that for the same reason. Okay, so it's not in the tables. Is there a special manipulation? And the answer is yes. So in general, what you'd probably do is you'd probably, like if I was given this, I'd be looking, oh, that looks a little bit like 1 over a squared plus x squared, which is equal to 1 over a inverse tan of x over a. But what you're kind of thinking of, oh, I have some techniques in this module that I'm learning. One of them is complete the square. But what's going to happen is it is going to be a complete the square. So rather than x, it's going to be what will later be called a shifted x, x plus b. Okay, so what we really want to do is write the x squared minus 12x plus 41 in that form. Okay, so first we're going to complete the square. So we want to write x squared minus 12x plus 41. We want this to equal, so it should be a squared plus x squared, but we've got a shifted x, so instead of x, it's x plus b squared. Okay, so what we said above was you multiply out the right hand side. And compare. So we want to get all the x squareds together. That's x squared. Then the x's, 2bx, and then the constants a squared plus b squared. And we're going to compare the left hand side and the right hand side. So, not a good choice. So, they both have an x squared. Like if one of them had an x squared and one of them had a minus x squared, it had gone wrong. Okay. What is the multiple of x on the left hand side? Minus 12. On the right hand side, 2b. So the things in the squares have to be equal. And what are the constants? 41 and a squared plus b squared. So what I have to have is 2b equal to minus 12. And I need a squared plus b squared equal to 41. So let's see how this goes. So the equation on the left hand side is very easy. Divide both sides by 2 to get b is equal to minus 6. And then you can put in the b is equal to minus 6. Maybe go this way. A squared plus, what's minus 6 squared? Minus 6 by minus 6 is plus 36. take away the 36 from both sides, and you get a squared is equal to 5. And then take the square root of both sides. So a is equal to the square root of 5. Now once again we have the issue. Technically there are two solutions to this algebra problem, plus or minus, but you only need the minus one. So we can rewrite x squared minus 12x plus 41 as a squared, which is square root of 5 squared, plus x plus b, x plus minus b, which is the same as minus 6 squared. So what we're dealing with now is in fact this integral. Now if you go with the very naive, and I'll tell you what I mean by naive. So you're comparing this with antiderivative 1 over a squared plus x squared dx is equal to 1 over a inverse tan x over a. So if you want to just use that straight away, here you will get the right answer. There are different occasions so one of the things I could do is I could give the things on the bottom, say if they're all multiplied by 4. Now what really you should do is you take out the 4 out of the bottom, and it reduces to what we had. Now actually I can just make this a little bit easier. So you can take out a common factor of 4 out of the bottom. It'll be division by 4, which is a quarter, so it'll be quarter I. Alternatively, you could actually complete the square, but you'd have a 2x all squared. So this thing should be something like 2x maybe minus 12 squared plus maybe 2 root 5 squared. So something like that. So instead of x minus 6 as we have, you somehow end up with 2x minus 12. Okay. So I'm saying that this is, so suppose that happened, or if I just gave you that. Now you cannot use the formula directly there. You'll end up with the wrong answer. And so what I'm kind of saying is that if you just use that blue formula here, so instead of x, you have x minus 6, I will give you full marks, but I want you to know that it's a bit dangerous. Really, you should do a little substitution. So the manipulation has rewritten it. It's not in the tables yet, really, because it should be x squared. So you should do a little substitution, in my opinion. So we'll do the substitution. So the substitution would be, here is a function, here is a multiple of its derivative. Alternatively, you do liate. Now, if you did the whole of the bottom, that would just simply be incorrect. Maybe it's a special substitution that you see here. However way you cut it, the substitution should be w is x minus 6. If you carry out the w substitution, differentiate both sides, you get dw dx equal to 1. Multiply both sides by dx, you get dw must be dx. And so we'll put this thing back together. Can't remember the colors I used to use. Root 5 squared plus, so now the x minus 6 is w squared, and the dx is dw. And now that is in the correct form for the formula in blue on the right. So now I can use the formula on the right. Now what's the a? The a is root 5, because that's the thing, the constant that's squared. So I get 1 over root 5 inverse tan. So my variable here is w over a, which is root 5. Now I won't get full marks here because I was asked to anti-differentiate with respect to x. So I put w back in terms of x, and also you need the plus c. So you get 1 over root 5 inverse tan x, sorry, what's w? X minus 6 over root 5 plus c. And there we go there. Okay. And I think we're going to push on and do another example here. So here, there's no direct integration in the tables. There's a possible manipulation. If you try and do w is like 15 plus 2x minus x squared, you're going to lead into nonsense. You'll end up with w's and x's or u's and x's depending on how you do it. Now what we have here is, it looks a little bit like an inverse sine, but as we said, it's a shifted one. Now this is a harder problem for the day students where they have an unseen exam, but I mean you have the notes in front of you, so you can prepare you know, that if it's a 1 over square root minus x squared, I think I kind of summarize this here. So if you have 1 over square root of minus x squared, it's an inverse sine. You need this a squared minus complete the square. And if it's a 1 over x squared plus, you need the inverse tan, which is a squared plus. So this is probably what you'll be running with into the exam. Okay, so we're going to complete the square in this fashion. So 15 plus 2x minus x squared, we want this to equal a squared minus x plus b squared. Now we have to be careful with the sign here. So what I recommend is something like this: a squared minus, and then x plus b squared is x squared plus 2bx plus b squared. And then you see the minus multiplies all of them. So you have to be a bit careful here. So on the left hand side you have constant first. So let us do constant first as well. So you get a squared minus b squared. Constant. Then x. So it's minus, look at this, minus 2bx. And then finally minus x squared. So now we compare. So we've got a good matching with the minus x squared. You really should check that, because like say you did a squared plus, they wouldn't match, and what you're doing would be nonsense, and you should start again with a squared plus. Then the multiple of x is 2 and minus 2bx. And then finally the constant here is 15, and the constant here is a squared minus b squared. So first of all, we're going to say minus 2b, the multiple of x on the right hand side, must equal 2, the multiple of x on the left hand side. Divide both sides by minus 2. B is equal to minus 1. Okay, then we're looking at a squared minus b squared is equal to 15. We know that b is equal to minus 1. So what's minus 1 squared is minus 1 by minus 1 is plus 1. So we have a squared minus plus 1, in other words a squared minus 1, is equal to 15. Add the 1 to both sides. So get a squared is equal to 16. Then do the square root of both sides. A is equal to the square root of 16, but again we have to be careful. In general there are two solutions here, plus or minus, but we can just choose the positive one. We can just choose a equal to 4. So this isn't exactly an implication, but we can choose it. So we have found that 15 plus 2x minus x squared can be written as a squared, which is 4 squared, minus x plus b, which is x minus 1 squared. So we can rewrite what we had initially, which is integral 1 over the square root of that thing on the left, the 15 plus 2x. Is that actually what we had? 15 plus 2x, yeah. But instead of the 15 plus 2x minus x squared, we'll put in the 4 squared minus x minus 1 squared. Now you can use the formula right away. We'll write the formula down the bottom here. So this one says that if you have antiderivative square root of a squared minus x squared dx, this is equal to inverse sine of x over a. Okay. If you use that straight away, but instead of x you get x minus 1, you'll be okay. I'll try and be a bit more careful, and I'll try and do a w substitution. W is equal to x minus 1. You differentiate both sides. With respect to x, you'll get dw dx is 1. Multiply both sides by dx, you end up dw is equal to dx. So I'm going to rewrite this as square root 4 squared is fine, minus w squared, and the dx is equal to dw. And just missing the w squared. So now this is in the tables. And see, so we're looking at the blue formula in the bottom right of the screen, and the antiderivative 1 over squared 4 squared minus w squared. You have to be able to see that the a squared 4 squared pattern spotting. If pattern spotting is a difficulty, all you can really do is just do more questions. Look, let's be honest here, this is, well, in my opinion, this is the hardest thing on the whole thing. So I mean, don't feel bad if this is very difficult, but for the rest of us, like, you have to be able to spot a pattern like that. You have to see the similarity between what I've written here and in the bottom right hand corner. So anyway, this is ready to go. So the antiderivative, this is inverse sine w over 4, and as before, we were originally asked to antidifferentiate with respect to x, so we should put the w back in terms of x, and we should do plus c. Okay, so we're going to do one more example. Makes a long lecture, but you can pause it, of course. So see, we got an integral with limits. If, in my opinion, if you have an integration by parts, or if you have one of these here, to complete the square, you should just forget about the limits initially and just do the antiderivative. So I think that's what's going to say in the next page. Ooh. So there's supposed to be loads of room here to complete the square. So I'm going to forget about the limits, and we're going to talk about 1 over x squared plus 6x plus 16. So I don't have much space here, right? So we're going to have to do this in really small space. And I'm going to do it quite quickly. I'll leave it kind of as an exercise, really. So you're trying to say that x squared plus 6x plus 16 is to be equal to a squared plus x plus b all squared. That gives you x squared plus 2bx plus a squared plus b squared. And we want 2b to equal 6. And that means you want b to equal 3. And you want a squared plus b squared to equal 16. And if b squared is, if b is 3, b squared is 9. Take away 9 from both sides. You want a squared to be 7. You end up with a is equal to plus or minus square root of 7. So what you're ending up with, this thing, is antiderivative 1 over, so instead of the x squared plus 6x plus 16, it'll be the a squared, which is root 7, plus x plus b, x plus 3, all squared. And this is the inverse tan one, which we'll just write down the formula here. So the antiderivative of 1 over a squared plus x squared dx is equal to 1 over a inverse tan of x over a. And if you use that formula here with instead of x plus 3, it's okay. It's just the worry be if instead of x plus 3 you have 2x plus 3, then you can't use that formula directly. You shouldn't really use it. You shouldn't really do it with x. It should be with x all the time, but I'm just saying you do get away with it, as our substitutions are showing. So how would I do that integral there? I would recommend, now we can actually bring in the limits now, I think, temporarily anyway. So I would do a little w substitution equal to x plus 3. So if you do that, you end up with, now if you're going to do a w substitution, I recommend forgetting about the limits until you go back to x. So we have 1 over the square root of 7 squared plus w squared and the dx was equal to dw. Okay, this can be antidifferentiated directly as it is. So we get 1 over a. Now here the a is root 7. You'll have to go back. Where are you getting the a? So the a squared, the thing that's squared, the constant that's squared is the a. So here I have root 7 squared, so that's the a. Inverse tan w over root 7. Now I have to go back to use the limits, which were minus 2 and 1. I have to go back in terms of x. And the x is, or sorry, so the w is x plus 3. So we get 1 over root 7 inverse tan w is x plus 3 over root 7. Numbers here are horrific. And we're going from minus 2 to 1. Okay, so we do top limit minus bottom limit. Now what's very important here is you have to be in radians. So inverse tan x plus 3, so top limit 1 plus 3. As I said, you have to be in radians here. Minus 1 over root 7 inverse tan, put in the x equal to minus 2. Now I'd be happy not to have to put that into the calculator, but it's not there. So this is, we'll probably round this to 4 significant figures. So I get, am I in radians? You have to be in radians. 1 over root 7 times inverse tan 4 over root 7 minus inverse tan 1 over root 7. So it comes out as 0.2362. Now remember that integration is finding area. So this is the function in question. This is the y is equal to 1 over, what was it? X squared plus 6x plus 16. And so if you integrate this function between minus 2 and 1, you find that area. What's a good exercise is to estimate this area using, you know, triangles and rectangles and compare. It's a bit of crack now. The lecture's gone on for too long, so I won't. Okay.